Today's lesson is an introduction to propagation of uncertainty. For this lesson, you're going to need to use your pink data collection and analysis practice workbook. If you're accessing this document from Schoology, it's called collective documents for data collection and analysis practice or something like that. Okay, so it's a pink workbook that you have received. Other information for propagation of error can be found in the green guide to writing lab reports. So both of those documents will be useful to you as you begin to learn about propagation of uncertainty and doing the practice problems today. So to start this lesson, we're going to tell a story of America's Biggest Loser. So in this game show, you can win $1 million if you lose 12 pounds in the next 30 days. So we have a contestant who initially weighed 152 pounds, plus or minus 2 pounds, according to her scale, and 30 days later weighed 141 pounds, plus or minus 2 pounds. Does she win the $1 million? So the deal was she had to lose 12 pounds. And if we look at the 152 and the 141, we realize that that does not come out to a loss of 12, it comes out to a loss of 11. But what we want to consider here, being the diligent scientists that we are, is there was some uncertainty in those measurements. And so my question is, what was the most weight that she lost or the least amount of weight? So if we think about the most weight that she could have lost, let's say her initial reading of 152 was actually 154, okay, so the plus 2 pounds. And then the final reading maybe was 141 minus 2 pounds, so 139. In this case, the contestant would have lost 15 pounds, okay, which definitely qualifies her for the prize. All right, now the least amount of weight that the contestant might have lost. So maybe initially, instead of 152, we did minus 2, she weighed 150 to start with. And her final weight was 141 plus 2, 143. In this case, using those numbers, she only lost 7 pounds. So the question is, within our range of uncertainty, did she lose the 12 pounds? And then the answer would have to be yes. Okay, based on the measuring devices we used, she lost somewhere between 7 and 15 pounds. So she wins the prize. So we express this range of uncertainty in this way, that the total weight lost was 11 pounds plus or minus 4 pounds. Now, I'm not sure if this would fly on network TV, but I think based on the measuring devices that we use, she should win the money. Okay, so now we're going to apply this idea of uncertainty in measurements and calculations to lab data. So I'm going to have you look at that pink data collection workbook, and we'll do some practice problems within that. Okay, so we're going to start with page 2, which is a little bit of vocabulary that you're going to need in our discussion. So we can all be speaking the same language. And I'm going to try to zoom this just a little bit because it's very small on my screen. All right. And you can follow along again on your page 2 in your workbook. Okay, so error, some of this vocabulary, error describes anything that causes a measurement to be different from the true value. And we've encountered this before when we've talked about percent error, right? So percent error tells you how high or how low your answer is compared to the true value. We also have errors, though, that come from uncertainties in our measurements. And those are the ones we're going to be focused on today. So uncertainty in measurements can be expressed, and calculations can be expressed in 2 ways. They can be expressed as absolute quantities. All right, this is based on the same unit that you measured in. So for example, if you take the volume of a liquid and say that it's 13.2 milliliters, you would note that the uncertainty in your measurement, your estimated digit, is always that last one, the 10th place. And so you would say, I don't know, it could be 13.2, 13.3, maybe it's 13.1. So your absolute uncertainty is plus or minus 0.1 milliliters. When we did the measurement lab, I asked you to record these uncertainties. So you're familiar with absolute uncertainty already. The other way that you might express the uncertainty of a measurement as its percentage related to the measurement itself. I call that percent uncertainty usually. And what you would do with that is take your absolute uncertainty, 0.1 milliliters, divide it by the 13.2 milliliters, multiply by 100 because it's a percentage, and that would give you percent uncertainty. So my measurement is 13.2 milliliters plus or minus 1% of that value. We're going to need to be able to express both absolute and percent uncertainties in the work that we're about to do. The last thing I want to point out to you here is a little definition of percent error. You're already familiar with this. Percent error is a measure of accuracy. And uncertainty, the uncertainty is a range, like that 7 to 15 pounds that we were talking about, the 11 pounds plus or minus 4 in the previous example. So there's a variety of other terms defined here on page 2, but for now we're going to move on to the work of doing the calculations. So on page 3, top of page 3, we're going to go over first the rules that we use for propagating uncertainty. So our goal here today is to state uncertainties in both absolute and percentage form, and to determine overall uncertainty when we do a calculation. So there are 2 rules that we're going to follow for this. The first rule is when you add or subtract data, you add the absolute uncertainties. And in rule 2, when you multiply or divide data, you add the percent uncertainties. Okay, so down below that, here and here, are again examples. What do I mean by absolute uncertainty and what do I mean by percent? Okay, so shouldn't be too hard, right? We're only going to use 2 rules. So let's see how this works. I have an example that's worked for you at the bottom of page 3. Suppose you want to do the following calculation. I want to know what X is, and we know we have A, B, and C as our variables, and their values, their measurements are given. So the first thing you do in any single one of these problems is do the math, all right? Do this as if it's just a regular old math problem. So we're going to take A minus B plus C, and in this problem, we calculate that X equals 8.12 grams. All right, so nothing tricky so far. Now, do we know that that answer is exactly 8.12 grams? Well, no, it can't be because our measurements that we started with were not exact measurements. They have uncertainty associated with them. So now we follow our rules and we propagate uncertainty. We carry it forward. So rule 1 tells us when adding or subtracting data, we add the absolute uncertainties. So for X, the absolute uncertainty in A was 0.01, B was 0.01, and C was 0.01. So we add those uncertainties together, and the uncertainty in X is the sum of those, or 0.03 grams, plus or minus. In order to calculate our overall percent uncertainty in X, we take our absolute uncertainty, 0.03, divide it by our value, 8.12, and express it as a percentage, okay? And you can see here that I have included 2 sig figs in my percentage, which if you're carefully following sig fig rules, you might decide, oh, I only need 1 sig fig there. And what I'll tell you is that we have one additional rule that is helpful when it comes to sig figs. And it's really the main sig fig rule when dealing with propagation of uncertainty. The protocol is when you calculate the overall percent uncertainty at the end of your problem, if it's greater than or equal to 2%, it only gets one sig fig. If it's less than 2%, it gets 2 sig figs. So ours was less than 2% overall, so I gave it 2 sig figs. All right, so that is the process. That's how you propagate error. Those were the calculations we did, and we considered the error in each of our measurements and carried that forward to the answer in our calculation. So now, how do we present that information? Top of page 4. You can express your answer with both percent uncertainty overall and absolute uncertainty. And we like to use a visual aid to demonstrate that. So on this visual aid, I've put my answer, 8.12 grams here. I've added the absolute uncertainty and subtracted the absolute uncertainty from that. One thing to notice here is that the place value of your answer, the hundredths place, should match the place value of your absolute uncertainty, because if you're adding them together, the result has to be represented to that same place value. Okay, so there are some sig fig considerations when you do propagation of uncertainty, but it's also a little bit more relaxed, as you'll see in some of the examples. So up until this diagram represents our propagated uncertainty, or sometimes we say propagation of error. If we know that the true value of this mass measurement is actually 8.59 grams, we could also do a percent error calculation, which you're familiar with, which is shown here. And you can see here that our answer was too low. In fact, our range of uncertainty does not contain the true value. The true value is higher than anything in our range. And so in this case, our percent error is much greater than our percent uncertainty. And we'll use that when we start to talk about error analysis and conclusion writing later on with lab data. Okay, so now we're ready to try a problem together. And what I'll ask you to do is I'm going to go through the problem start to finish, but I will ask you to pause and fill things in and check your answers as we go. Okay, so now we're going to do a volume calculation. And so we're given the following data: length, width, and height of a cube. It would be a block, I guess. A cube would have the same length, width, and height. And so in order to calculate the volume, we would multiply those values together. So just like you would in any mathematical approach, we would do 5.35 centimeters times 3.22 centimeters times 2.11 centimeters. We'd multiply those together on your calculator. So do that, pause and do that. And you should get 36.3 cubic centimeters as our answer. Okay, so I'm going to put that right here in my block because I already know the answer without propagating uncertainty. So now you go back and you look at the steps that you did to get your answer, and you can see that we multiplied and divided. And so the rule when multiplying and dividing is to add the percent uncertainties. So in this problem, you're only given absolute uncertainties. So your next step is to convert those to percentages. So I will demonstrate with the length. We're going to take the absolute uncertainty, 0.05, and divide it by the length, 5.35 times 100. That's going to give me the percent uncertainty in my length. And I'm just going to have you pause here for a second and look at my number. you might think that I should just put one sig fig over here in my percent uncertainty because of the calculation that I'm doing. But I would like you to consider keeping one extra sig fig each time you do this. And then at the end of the problem, we'll deal with rounding to the correct number of sig figs. There's not only one correct way to do this, but this is the way that I will continue to do the problems, okay? So if you would just always give yourself an extra sig fig as we go, we'll match. So you should pause and calculate the percent uncertainty now in your width and height, and then check your answer with me. So now that you've calculated percent uncertainties, we now are going to propagate the uncertainty. We're going to carry those uncertainties through this calculation. And so when we multiply, we add the percent uncertainties. So I'm going to do 0.93 plus 1.55 plus 2.37. And when I add those up, I get an overall percent uncertainty of plus or minus 4.85%. And you know our rule is when you have greater than 2% overall percent uncertainty, you round to one sig fig. So that's going to give us plus or minus 5% uncertainty. I'm going to fill that in to my visual down here. Plus 5%, minus 5%. So you'll notice that we never added these absolute uncertainties together at any point in this problem. We didn't need to. We did need to add their percent uncertainties together. The final step of this problem would be to calculate the overall absolute uncertainty, so we can finish filling in our little table. Okay, so overall absolute uncertainty. The easiest way to calculate this is to say to yourself, what is 5% of 36.3? And mathematically, that tells me I take 5% in decimal form and I multiply it by my value 36.3 cubic centimeters. When you say 5% of, it means you take the decimal form of the percentage and multiply it by the number, 36.3. And in this case, I get 1.8 cubic centimeters. All right, what's important here for sig figs is that this number here matches the place value of that number there because we're going to add it. And so we want our answer to go to the same place value. Okay, so that's different than what you are used to doing with sig figs. It's actually a little bit easier. So if we add 1.8 cubic centimeters here, we should have 38.1 cubic centimeters as an answer. And over here, 34.5. And so our answer is in that range, plus or minus 5%. Okay, so those two problems were examples of using Rule 1 and Rule 2. And so on the next page in your pink booklet, page 5, we have some practice with using one rule. Okay? This is something that you should definitely pause because I'm going to work through the problem, but you will be working through it at your own pace. So as I talk about the steps that we're going to do, you should pause and do those steps. So solve for W when W equals K plus L. So first the math. W equals K plus L. So go ahead and do the math. I'll put my answer down. And I'll also record that down here in my visual. So first do the math. then propagate the uncertainties. Okay, so a lot of times people like to make a little table like this to propagate uncertainty, a chart. That's a great way to keep your work organized. It doesn't have to be in chart form, so that's up to you. Absolute uncertainty. So according to our data, this is plus or minus 0.0001 gram. This one is also plus or minus 0.001 gram. Then you ask yourself, what operation mathematically am I doing in this problem? I'm adding K plus L. I got the answer 0.0533 grams. So how do I propagate uncertainty for that calculation? Because it's an addition problem, I add my absolute uncertainties in K and L. And I'm going to get an answer of 0.0002 grams. Okay, so now I go back down here to my visual. I'm going to add plus 0.0002 grams. I'm going to subtract 0.0002 grams. And I'm left with the final answer, 0.0535 grams. And over here, 0.0531 grams. So it kind of looks like I'm done. I've solved this problem. I know what my range of uncertainty is. In order to be fully complete in presenting our visual at the end, we want to fill in these circles. So we want to know the overall percent uncertainty for our answer. So remember, percent uncertainty is absolute divided by the number times 100. And for this problem, I get plus or minus 0.38%. So my overall percent uncertainty is less than 2%. So I keep the 2 sig figs and fill in my chart. You can see at no time did I ever need to use percent uncertainties for these two values, K and L. So don't waste your time calculating them. They're not needed for this problem. Okay, so here's my final answer. Let's try simple propagation of error, problem number 2. Next page. In this problem, we're going to solve for V. V equals M over N minus P. Let's do the math. N times P. 10 seconds times 9.5 seconds. Go ahead and do the math. Pause me so you can check your answer. Meters per second squared are the units. So this is like an acceleration value possibly that we calculated. And so I'm going to now get ready to propagate uncertainties for that. So you see that I'm given absolute uncertainties for each of my values. So if you'd like to compile them in the table, that's a helpful way to organize things. And then I consider the math that I did. And so I multiplied and I divided to calculate V. And I got the answer of 0.38 meters per second squared. So how do I propagate uncertainty for that calculation? So when you multiply and divide, the rule is to add the percent uncertainties. So that means if we're going to do that, we have to calculate all the percent uncertainties over here of the numbers that we multiplied and divided. So pause and do that. You'll see when I calculated my percent uncertainties, I allowed all of them to have an extra sig fig because now that I'm going to calculate the uncertainty for V, I'm going to add those all together, 0.55 plus 5.0 plus 5.3. And when I do that, I get the answer of plus or minus 10.9%. So this number is greater than 2%, which means I'm going to round it just to 1 sig fig. So 10.9 rounded to 1 sig fig, that's rounding to the tens place, is plus or minus 10%. Then to calculate the absolute uncertainty, I'm going to do 10% times my value, 0.38, and I'm going to get plus or minus 0.04 meters per second squared. So the reason why I'm going only to the hundredths place here with 1 sig fig is because I know I'm going to have to add that to my value 0.38, which only goes to the hundredths place as well. Now let's use the information that we calculated to fill in our table. To fill in our visual at the bottom. So plus 10%, minus 10%, plus 0.04 meters per second squared, minus 0.04 meters per second squared. When we add that in, we should end up with 0.42 meters per second squared and 0.34 meters per second squared. And that's our range of uncertainty. Now I know I am going to get some questions about sig figs and propagation of error. You have to relax your sig fig rules when you're doing propagation of error. That will make it a lot easier for you if you can just relax those rules and use them only where they apply here at the end, okay? That we have 1 sig fig when we're above 2%, and that the sig figs, the place value in our absolute uncertainty matches the place value in our answer. Okay, so we're going to take this up a notch and we're going to talk about problems in which there are multiple operations going on where you have to use all your sig fig, all your propagation of uncertainty rules. So on page 7, let's look at an example. So here's a problem where we're going to calculate x, and x is equal to a times the quantity b minus c. So the first thing we do is we solve for x. And when we do the math, I'm going to encourage you to show this step right here and this result, because we're going to be using it when we propagate uncertainty. So in your order of operations, when you see a problem like this, you always subtract first. So we subtract and then we multiply. And here you can see that my answer, 1030, is rounded to 3 sig figs because of that value right there. Okay, so the 8.40 leaves us with 3 sig figs in our final answer. So now what we want to know is, what is the uncertainty in the 1030 square centimeters? So you go back to the math that you did. The first thing we did was subtract b minus c. So when you add or subtract, you add the absolute uncertainties. So we take the 0.02 and the 0.05 and we get 0.07 is our uncertainty in b minus c. The next piece of math that we did is we multiplied a times b minus c. When you multiply or divide, you add the percent uncertainties. Okay, so percent uncertainty for A is 0.5 divided by the value of A times 100 is 0.4%. In B minus C, we take the absolute uncertainty of 0.07. We take the value of B minus C, 8.40, divide by that, times 100 gives me 0.8% uncertainty. So if you want to know the overall percent uncertainty in X, you add the percent uncertainty in A plus the percent uncertainty in B minus C for a total overall percent uncertainty of 1.2%. Then to calculate your overall absolute uncertainty, you determine what is 1.2% of 1,030. Okay, so the way you can do that is take your percentage and turn it into a decimal. So that represents 1.2% times 1,030. And remember that the 1,030, the tens place, is our most precise decimal place. Most precise decimal place. And so when we get our answer here, we want to round it to the tens place. Because you can see below in the visual, we're adding 10 to the 30. And so you can see that the place value for all of those has to be the same when you're adding. The true value for this problem is 1,057. It's outside of our range of uncertainty. And when I calculate my percent error, I can see just how accurate I am. And my answer is too low by 3%. This is another example where my percent error is greater than my percent uncertainty, which tells me that I have an accuracy issue. My measurements say it should be somewhere between 1,020 and 1,040, but the true value is actually considerably higher than that. So we know that there's some systematic error leading to our value making it too low. All right, so we're going to practice one of these more complex ones together now. So on page 8, we're going to look at problem number 3. All right, and so again, please pause throughout this video to practice this, fill this in on your own. Don't just watch me, but actually participate and do it. That it'll become more straightforward for you as you do that. So in this problem, we're solving for y. Mathematically, what would we do? Well, we'd do this in 2 steps. First, we'd add d and e, right, order of operations. I'm going to get rid of units while solving this problem just because it will clutter things up a little bit. So I'm going to add my numerator. Then I'm going to divide by my denominator. So this is the answer to my problem, 1.81 centimeters per second. However, we had uncertainties in the values that we used to calculate this. So we need to now propagate those uncertainties, carry them forward. So I'm going to transfer the absolute uncertainties here from above into a table, just so I have everything in the same place. Okay, so now we think about the math that we did. So the very first step was us adding d plus e together. And when we did that, we got the value of 27.2 centimeters. And when you add 2 pieces of data, you add their absolute uncertainties. So 0.1 plus 0.1. My absolute uncertainty in my numerator is plus or minus 0.2 centimeters. The next step of the math was to calculate y. And the way I got y was I took d plus e and I divided by f. Okay, so when I did that, I got the answer 1.81 centimeters per second. And since I divided, I need to add the percent uncertainties of d plus e and f. So pause and calculate percent uncertainties for those values. I'll write mine in. So you'll see that I've calculated the percent uncertainty in F and the percent uncertainty in D plus E. That's my numerator and my denominator. And so when I divide, I'm going to add the 3.3 and the 0.74. And I'm going to get 4.0%, which is greater than 2%. So I'm going to round that to plus or minus 4% uncertainty. Okay, so then we need to take that number and calculate our absolute uncertainty. And so the way that we do that is to take our percentage, 0.04, and multiply it by our value. Again, we want our overall absolute uncertainty to go to the same decimal place as our data. And so when we do that calculation, you should get plus or minus 0.07 centimeters per second. You'll see at no time did I ever calculate percent uncertainties for D and E because I never needed them, right? D and E were first added together, and then that value was used in a division problem. So you only calculate absolute uncertainty and percent uncertainty when you need them for carrying them forward in the calculation. So my final step now is just to translate all of this to my diagram. So I'm going to put my answer, 1.81 centimeters per second, plus 4%, minus 4%, plus 0.07 centimeters per second, and minus 0.07 centimeters per second. And then I'm going to add and subtract to get my range of uncertainty. So today you've seen examples of calculations where we just add data together, subtract, multiply and divide, and then combinations of those operations. There is another practice problem, number 4, on page 9, and your homework is going to consist of simple propagation of error problems 5 and 6. So you'll have lots more practice with this. Please watch this video again with pausing if you need to review any of the things we've gone over, and you can also refer to your green guide for more information on propagation of uncertainty. Have a great day. Thanks, guys.